Okay, so we're gonna go ahead and get into electrochemistry. This one isn't too long, so I'll see if I can just kind of summarize it for you guys. The whole basis of electrochemistry is basically a process called electrolysis. Electrolysis is when electricity is passed either through a solution or a molten ionic compound or an electrolyte, and where this chemical reaction occurs. What you see here in the image is an example of a voltaic or an electrolytic cell. So here's the way it basically works, okay? Here you see that you have a molten solution of NaCl. All right. Now, you have two different areas here. One is called the cathode and one is called the anode. Now, the anode, okay, this is a part of the voltaic battery or the electrode where oxidation occurs. If you don't remember oxidation and reduction, go ahead and look at that video on redox reactions. And then the other side is the cathode. Okay, the cathode is the electrode where reduction occurs. Okay, so remember, oxidation is basically losing electrons, and reduction essentially is gaining electrons. Okay, so if you take a look here, right, what's going on here in the electrode at the anode, you can see that chlorine is in its ionic state, right? In the solution, you can see it here, it's got a 1 minus. And basically what's happening here is that chlorine is giving away its extra electrons. You know it has extra electrons because it has that minus, right? Now, because you have 2 moles of chlorine, these 2 moles of chlorine are going to give up 2 electrons. So essentially it's reducing. Now, as this current, the source of this current, right, this is basically a complete circuit up here. Complete circuit. Okay, and what's happening is these electrodes are causing this solution to basically go through a redox reaction. Okay, so let's take a look at that reaction. If I was to write this redox, it would look something like this. You can see that Na plus, this is in liquid, right, is gaining electrons to become metallic sodium. All right. And then you see that the chlorine, the 2 moles of chlorine, 1 minus, are becoming chlorine to form form 2 moles, to form Cl2 and pick up those 2 electrons. Okay, so where we're at here is basically this is your cathode and this is your anode. All right. That's basically how a voltaic cell works. It's to direct current. These things happen in the same solution, and you have this oxidation reduction reaction happening. Let's go ahead and take a look at another example. Here we have another example of a voltaic cell. Okay, again, a voltaic cell is going to be characterized by everything happening in the same container. So everything here is in the same solution. Now, in this case, the solution that we have is going to be a nitrate solution, right? So the solution here, even though it's not labeled, is actually potassium nitrate. Okay. So what's happening here? So what's happening here is similar to what happened in the other battery, where you have a cathode that is undergoing reduction, and then you have an anode that's undergoing oxidation, right? The anode is here, the cathode is here, and you can see that the byproducts are going to be the hydrogen and the oxygen gases. So let's take a look at the difference between what happens when you have an ionic solution and an aqueous solution over here, like you have potassium nitrate. So this is the reaction that we did earlier, right here. Now, remember that the amount of electrons that are oxidized and reduced must equal each other, right? So we're going to go ahead and balance this reaction to get the net ionic equation. I don't know if you guys remember how to do that, but here it goes. So if I have Na plus, well, you know what I can do? I can just do it over here. So what I'm going to do is I'm going to balance these, right? So because this one has to be balanced, I'm going to go ahead and multiply everything in this one by 2, right? To get those electrons to equal. So if I bring it over here, it's going to be 2 Na, 2 electrons to produce. Okay. And then these are already set up in this way. Okay. Now, when we combine these two reactions, right, you're going to combine everything on the left. And then everything on the right. Okay, if you have the same number of electrons on both sides, these are going to cancel, right? When those cancel, you're going to end up with your net ionic equation, which is just going to be liquid plus 2Cl minus produces, okay, okay, and this here is going to be known as the cell reaction. Okay, the cell reaction, in no simpler terms, is just the net ionic equation of the redox. So when we did redox reactions, right, we identified the oxidation, we identified the reduction, we wrote the half reactions, and then we balanced the electrons, right? The cell reaction is exactly the same thing. So if you get a question asking you to provide the cell reaction, this is basically it. All you're going to do is write the net ionic equation of the redox reactions that are happening in this solution, or in this chemical process. In a voltaic cell that has an aqueous solution or in an aqueous environment, right, here's the difference, right? So at the cathode, what we're seeing is that water is actually being reduced, right? So what that looks like is you're going to have 2H2O, right, plus those 2 electrons to produce hydrogen gas, right, plus 2OH minus, okay? What's happening at the anode, right, is the anode is actually being oxidized, but it's oxidizing water. So in an aqueous environment, right, we having the same oxidation and reduction, however, it's all happening with water. So this one kind of looks like this. O2 gas, right, plus 4H plus 4 electrons. Okay, so you're still getting oxidation and reduction. However, when you're working in an AQ environment, which is what we have here, okay, all the oxidation and all the reduction is going to occur at water. So if we wanted to balance this out, right, we would have to multiply this reaction by 2, right, and then write the net ionic equation. You do that, you add them all up, you cancel the electrons, and basically what's happening here is you're going to end up with 2H2O. Electrolysis happens here, right, to to form 2H2 plus O2 gas. This is also gas, okay? So this would be the net ionic equation that happens in the voltaic cell when you're working with an aqueous solution, okay? In this case, you can take a look at the diagram. You can see the reduction, you can see the oxidation happening, and then you can see that it's basically the same principle. The only thing that happens in an aqueous environment is all these reactions happen in water. Now, when looking at this reaction, right, it's easy to kind of say, well, wait a minute, if everything's happening at the water, then what's the point of the potassium nitrate? So you still need these ions, right? You still need these ions to help facilitate the transfer of electrons, because if it was just in pure water and there was there's no salts in the water, then nothing would happen. The reaction just wouldn't move forward. And you can see by the diagram here, right? You can see here that as the reactions are happening at the anodes and the cathodes, the salt and the ions, for example, the potassium is being attracted to the cathode in this direction, right? And then the nitrate, which is negatively charged, is being attracted to the anode in this direction. So even though the redox is happening at the water, the result of the redox does draw in the different salts. And as a result, the salts will also undergo a redox. So to give you an example, right, let's go ahead and take a look at a question here. Okay, so if I have, let's say into this solution, I added something like copper bromide. Where's my... All right, copper 2 bromide. All right, so here's what happens, right? If I was to add this into mix it with a solution of copper bromide and it's electrolyzed, then the cathode, which is this one here, starts to get coated with a reddish brown deposit of copper, and then that's where the positive goes, right? And then on the blue, excuse me. Sorry, I had a little bit of a blank there. At the anode, exactly the opposite happens, right? So the copper begins to kind of go around this area, right? And then on the anode, then you start to get a bromine attracted to this area, right? So then you start to get a kind of a precipitate there. So even though, again, the redox is happening at the water, the solution does play a part in the electrolysis. So let's kind of go over how that goes, right? Let's say you have potassium bromide is in electrolysis with potassium nitrate, just like we have here. Okay, so by looking at this, we can see and predict the products that are going to happen if the solution is made up of copper nitrate. This is the salt, right? This is where it's going to be, the electrolysis is going to happen. So what we're going to do is we're going to see if we can provide the net reaction. Okay, so we already said, right, that the cathode is going to be the reduction of the copper. So here we're going to write the half reaction. So copper 2 plus, this is aqueous, is going to reduce those 2 electrons to produce solid copper, right? That's that reddish brown material that you begin to see on the cathode. Then we're going to take a look at the water here. Okay, that's going to form the O2 just like we discussed earlier. Plus 4 electrons. Okay, so here we have it, right? So on one side we have the cathode, which is undergoing reduction. Then we have the anode. I think I've been misspelling this whole time. This is the oxidation of water. Okay. So what do? Right? Well, we have to balance the electrons, right? So remember that the amount of electrons that are being oxidized must equal the amount of electrons that are being reduced. So let's go ahead and balance those out. So I'm going to multiply everything in here by 2. When I set that up, I'm going to be left with 2 copper, 2 plus 4 electrons, yields to 4 copper, and then the second one is going to stay exactly the same. Okay. At this point, we can safely cancel our electrons. Okay. Once we combine them, then we're going to end up with our net ionic equation, which in this case is going to look something like this. That's aqueous, by the way. Plus 4H plus. Okay, so this would be the products that are formed in a voltaic cell that has an aqueous solution, and we're using copper bromide. The process is exactly the same. The only difference is now that we have to use that water. Okay, so let's go over this way, and that's what we see happening here. Okay, so let's take a look at something else, right? We'll get to this one in just a minute. Okay. So let's take a look at this copper that we see here. We said that copper 2 plus is going to reduce those 2 electrons to form solid copper. Okay, this is in solution, and then we have those 2 electrons. So what we see here, right, is this copper is picking up these 2 electrons. So in essence, what's happening here is 1 mole of metallic copper, which is this one, right, basically requires 2 moles of electrons to deposit to form this 1 mole of copper. Where am I getting the 2? I'm getting it from here. So what we're doing here is we're basically just using stoichiometry because it's a 2-to-1 ratio, right? If, for example, I had copper 2 plus 4 electrons to form copper, or 2 moles of copper solid, right? In this case, right, the ratio would be 2 to 4. For every 2 moles deposited of copper, I would need 4 moles of electrons. So 2 moles of copper needs 4 moles of electrons to be deposited, right? It's a simple stoichiometric ratio. All it is saying it's just a mole ratio between the amount of electrons and the copper that's produced. One thing that you may or may not see in your formula sheet is the Faraday, right? The Faraday is a unit named after Michael Faraday, which was the scientist that pretty much coined all these terms and did these reactions, right? So it looks something like a cursive F, and basically 1 Faraday equals 1 mole of electrons. So make sure to add this to your dump sheet there, so you have them in there. But Michael Faraday pretty much did the experiment, and he's the one that developed all of these experiments, right? And essentially, here's what he found out. To use the Faraday, right, we need to have it related to electrical measurements that can be used in the lab. So the SI unit of electric current, right, SI unit of electric current is called the ampere. It's abbreviated with the letter A. And the SI unit of charge is called the coulomb. And that's abbreviated with the letter C. The coulomb is the amount of charge that passes by a given point in a wire when an electric current of 1 ampere flows for 1 second. So what does all that mean? Here's what it means. It means that 1 coulomb is equal to 1 ampere times 1 second. Okay. If I wanted to write this, it would be 1C is equal to 1 amp times seconds. And you should have this formula in your formula sheet, okay? If not, it's pretty easy to remember. So here's an example. Here's an example of how this formula works. Let's say you have a 4 amp current. Okay, and that flows for 10 seconds. Okay. What is the amount of charge? So if I have 4 amps, so coulombs is equal to 4 amps times 10 seconds, multiply those two, then the charge that's passing at that moment is going to be 40 coulombs of charge, right? It's very, very simple formula to use. And this is how we tie in the Faraday, okay? So let's take a look at a question that says, how many grams of copper? So let's write this here. Okay, so how many grams of copper are deposited on the cathode of a voltaic cell? With 2.00 amps of current in a solution of copper sulfate for 20 minutes. Okay, so to work this problem out, obviously we need seconds, right? Because our formula says that we need seconds. So we're going to take these 20 minutes and we're going to convert to seconds. So I know that in 1 minute, there are 60 seconds. So that's going to give me a total of 1200 seconds. Okay. Okay, so now that we have the seconds, let's go ahead and multiply our charge. Let's find our charge, right? So I know that coulomb is equal to the amount of amps, which in this case is 2.00 amps, times 1200 seconds. All right. And if I multiply this out, I'm going to get that my charge is equal to 2400 coulombs. Okay, so where are we at? Now, I know that 1 Faraday is equal to 96,500 coulombs. This is a given amount, and that should be in your formula sheet. So if I know that 1 Faraday is equal to 9,600 coulombs, then I basically just have to convert here to Faradays. So I know that if I have 2,400 coulombs, and the conversion factor says that 1 Faraday is equal to 96,500 coulombs, then that's going to leave me with 0.0249 Faraday. Okay. From here, it's pretty straightforward. Basically, what we know is that we know that copper 2 plus is going to gain 2 electrons, reduce 2 electrons to form copper solid, right? So this provides us, the mole ratio says that 1 mole of copper is 2 Faraday. Or 2 Faraday is 1 mole of copper. Okay, so since we have our Faraday, okay, we're going to multiply by our ratio, which gives us that 1 mole of copper is equal to 2 Faraday. I know that 1 mole of copper is equal to 63.5 grams of copper, which gives us 0.791 grams of copper. Okay, so all this stuff works in unison, right? To figure this stuff out, you just have to kind of use a little bit of analysis and cancel units, and you're set up. make sure that you become very familiar with your formula sheet. I'll go ahead and stop the video here, and then we'll finish up with galvanic cells.